Welcome. We are looking at the engineering Bernoulli equation or macroscopic approaches to flow situations, analyze flow situations, design flow aspects. And we said that we need to find a friction factor for each situation for us to easily make sense of what's happening and to use whatever we know towards design and operation. Okay. So let us start looking at the friction factor for flow through a straight horizontal pipe. Let me show you how to get to that. I'm going to consider two major aspects before I get to that, or to get to that. Let us consider a well-developed flow through a straight horizontal pipe. Well-developed flow, the velocity at any point, at any radial position does not vary with length. So this is our, let us say, our horizontal pipe, the axis of symmetry, cross section 1, cross section 2. The engineering Bernoulli equation is typically applied between cross sections, macroscopic, right? Applied between cross sections. Here, if we apply the engineering Bernoulli equation between points 1 and 2, we get delta P by rho plus delta V squared by 2 plus G delta H plus FL hat plus WS hat equals 0. That's the engineering Bernoulli equation. This you can close your eyes and write down. And now if we cancel the terms, it's well-developed flow. The velocity here is the same as velocity here. Therefore, this term goes. There is no difference in height between the center point here and center point here from, let's say, a datum level. And therefore, Z1 equals Z2 and delta H tends to 0. There is no shaft work that has been included. There is no pumping work that has been put in. For example, any such work that is introduced is called shaft work. To understand it, to start understanding shaft work, let's say if there is a pump in the system, you could say that there is shaft work that needs to be considered. Till then, no. So what we have here is FL hat is nothing but minus delta P by rho for this condition, for this situation. One aspect. Equation 3.9.1-1. Now, even before I move forward, this is powerful. Note that we have made no assumption about the type of flow. Okay, it could be laminar, it could be turbulent, whatever. We never said or we never considered anything that represents the type of flow. Okay, all energetical aspects, there is no relationship to the mechanics of flow. Okay, it's all energetics of flow. So this is applicable irrespective of the type of flow, or applicable both to laminar and turbulent flows. That way it's powerful. In terms of use, it's very powerful. Now, we are getting to friction factor. To understand the process, let us consider a differential fluid volume in this pipe. A differential fluid volume which is representative, the shape of the differential element must be representative. Therefore, the differential fluid element that would be representative would be a thin disc of the same radius as that of the pipe, right? The thickness has to be very small and the radius has to be that of the pipe, and that disc is going to be a differential element for this flow situation. So a disc shaped, the differential fluid volume is disc shaped of radius r and thickness delta z. In other words, if this is a flow happening, this is the direction of flow, we take a disc of thickness delta z and radius r, and that would be a representative volume element, a differential volume element. If we draw the force balance, if we do a force balance on this liquid element, there is a pressure acting here in this direction. Okay, this is a free body diagram. Therefore, a pressure acting in this direction, a different pressure acting in this direction, which is different because of the length being different. And of course, there is a wall shear that opposes the motion, and that wall shear is going to act all along the circumference. So you have a pressure force acting this way, a pressure force acting this way, and a shear force a wall shear force that is acting in this direction, which is opposite to the direction of motion. So tau W is the wall shear stress both in laminar and turbulent flows. Even in turbulent flow, the layers closest to the wall will not flow at very high velocities. Therefore, there is a laminar layer, a boundary layer, it's called a laminar layer closest to the wall in fully turbulent flow. That's what is said here. Even in turbulent flow, the flow closest to the wall is going to be laminar. So let us do a force balance on the differential fluid element that is shown here. And therefore, if you do a force balance in a free body diagram that was drawn for the purpose, this is the direction, the positive z direction. Therefore, P times pi r squared is the area here, minus P plus delta P times pi r squared, minus, because this shear force is acting in this direction, shear force is nothing but the wall shear times the area of relevance. The area of relevance is the circumferential area of this element. That circumferential area is nothing but 2 pi r, the circumference, times the thickness, delta z, 2 pi r times delta z. So this force is nothing but tau W times 2 pi r times delta z. So this gives us a force balance that must be equal to 0 when there is no net force acting, and then you have well-defined flow conditions or well-developed flow conditions. Okay. So there is no net force that is acting on any fluid element or a representative fluid element. Equation 3.9.1-2. Therefore, you could write tau W or minus tau W as you take these to the other side, divided by 2 pi r delta z, you get this expression. If you reduce this, you have P pi r squared, you have minus P pi r squared, those two will cancel, and then you have a delta P pi r squared by delta z 2 pi r. So 1 r is going to get cancelled, pi will get cancelled, and therefore what remains is tau W equals minus delta P delta z times r by 2. In the limit delta z tending to 0, differential element we are taking, tau W can be written as minus d dz of P times r by 2. And which can be written as, this can be written as 2 tau W by r equals minus dP dz. So dP dz plus 2 tau W by r equals 0. Equation 3.9.1-3. And we can integrate this equation for a pipe length L between points 1 and 2 to get this relationship, which is more useful because these are measurable quantities. We can substitute, or most of them are measurable quantities. This can be estimated and so on. So if you integrate this, we're going to get between limits 1 and 2, points 1 and 2, we get P2 minus P1 by L plus 2 tau W by R equals 0, or tau W is nothing but minus P2 minus P1 by L times R by 2, which can be written as minus delta P by L times D by 4. This is radius, this is diameter. So you get this relationship. Or minus delta P is nothing but 4L tau W divided by D. So we have brought this to a relationship between minus delta P and tau W for a given pipe, for a given L and D. Now if you substitute this into 3.9.1-1, 3.9.1-1 was our engineering Bernoulli equation. Okay, let me show you that. Yeah, 3.9.1 for this situation turned out to be the frictional losses per unit mass equals minus delta P by rho. And if we substitute whatever we have derived into this, we get FL hat, fluid frictional losses per unit mass, equals 4 tau W L by rho D. Okay. Delta P you get delta P by rho is FL hat, minus delta P by rho is FL hat, minus delta P is this, therefore you get this. We'll call this equation 3.9.1-4. Now, we are ready to define a dimensionless parameter called the friction factor. We said this friction factor kind of unifies or gives a unified approach to various different situations. That's why we are interested in the friction factor. So friction factor we are going to define as Fk by A time divided by Ke dash, where Fk is the kinetic force, this is the area, this is the kinetic energy per unit mass. So fluid exerts a force on a body of interest. That force can be thought to consist of a static component and a kinetic component, Fs and Fk. And Fs is the force that is exerted when the fluid is stationary, and Fk is the force exerted when the fluid is in relative motion compared to the body of interest. Okay, this is the background for this Fk. Okay, the force acting on a body, the kinetic component due to fluid motion is called Fk. So you take you normalize it with respect to the area and then normalize that with respect to the kinetic energy per unit mass. Then, kinetic energy per unit volume. Yeah, please correct this. It is kinetic energy per unit volume is Ke dash. For a flow through a tube, the friction factor is Fk by A is nothing but the tau W. Okay, the shear, wall shear is representative of this. Kinetic energy per unit volume is nothing but what is kinetic energy? Mass into the energy related to the motion, and then you divide it by the volume. Half mv squared is the kinetic energy. So you divide that by the volume, the mass divided by the volume is density. Therefore, half rho v average squared is nothing but Ke dash. And from whatever we have derived, we know that tau W equals minus delta P by L d by 4. And therefore, we get the friction factor for this situation as, if you cancel out the terms, simplify this, minus delta P d divided by 2L rho V average squared. Okay. So this is the friction factor for flow through a straight pipe. We'll call this equation 3.9.1-6. Therefore, the wall shear is nothing but half from here. Wall shear is half rho v average times F. Okay, so this is a way of expressing the wall shear in terms of the friction factor 3.9.1-7. Now we substitute 3.9.1-7 into 3.9.1-4, which is this. FL hat equals 4 tau WL by rho d. Okay, if we substitute that, we'll get FL hat is 4, instead of tau W, we have half rho v average squared F L by rho d. So this turns out to be 4F L by d v average squared by 2. Okay. So the frictional loss per unit mass in a straight pipe is 4 times a certain friction factor, L by d v average squared by 2. So we have a means of predicting or calculating the frictional loss if we know the friction factor for a given pipe, for a given L by d situation, for a particular flow with a velocity of V average velocity V average. 3.9.1-8. So FL hat, the friction loss per unit mass, accounts for skin friction or the friction losses at the pipe wall. Okay. So the pressure drop that is being applied is used to overcome the friction losses, friction losses at the wall, and so on. So you need to provide energy for the flow to occur. It's one small insight that you can draw from this. Intuitive, but this one also tells you. So we can write 3.9.1-8 as, I'm going to rewrite this to get it of the form that is needed. So we can take this 4 down here and write f L by d by 4, V average squared by 2. Why am I doing this? I'm going to define something called a hydraulic radius as the cross-sectional area by the wetted perimeter. Once I define a cross-sectional area by the wetted perimeter, there is a possibility of extending this relationship to other geometries. Okay, there will certainly be a cross-sectional area for any geometry. There will be a wetted perimeter for any geometry. So if you can write this in terms of the hydraulic radius, then it is no longer limited to a circular cross-section. You could have a square cross-section as in the case of some AC ducts, and a rectangular cross-section as in the case of some AC ducts. Any cross-section, and then you could apply a similar equation. So let's write this in terms of a hydraulic radius. Hydraulic radius definition is equation 3.9.1-9. And for the pipe, the hydraulic radius is cross-sectional area pi d squared by 4. Wetted perimeter is pi d. So you simplify this, you're going to get d by 4. And therefore, if we write FL hat as F equal to F L by RH, V average squared by 2, that's what the earlier formulation said, then this equation can be used for any geometry. It can be extended to all cross-sectional geometries. So to find the friction factor for pipe flow, we typically use a friction factor chart, a Fanning friction factor chart that we normally use. Civil engineers use something called a Moody's chart, okay, which is somewhat similar. The definition of the friction factor is slightly different in a Moody's chart. I think it's 4F or something like that, but everything else remains the same. So this is the friction factor chart that you will find in the appendix of many fluid flow books. A simplified version of this has been given in your textbook, just barely necessary for our own needs. Okay, so here you have the friction factor F that we have defined for the flow through a pipe in the y-axis on a logarithmic scale, and the Reynolds number of flow on the x-axis again on a logarithmic scale. So it's a log-log plot. Till 2100, you can see this is 1000, this is 2000. So in a log scale, this is around this is 1000, this is 10,000. 2000 is somewhere here, right? It's a log scale, therefore it will be in the middle of this linear scale somewhat. So this is the region for laminar flow. Okay, and beyond 4000 is the region for turbulent flow. So in the laminar flow, you have this relationship between the friction factor and the Reynolds number. That relationship is 16 by NRE. So you could use friction factor of 16 by NRE and directly get the friction factor if you know the Reynolds number. For the turbulent regime, we definitely need to use the chart. We don't have this nice relationship. You could also use a chart here. This chart is the same as 16 by NRE. Okay, so no problem there. For the turbulent region, if you know the Reynolds number, and if you know something called a roughness factor in the pipe, the roughness factor is the thickness of the roughness level in the pipe, and the ratio of that to the diameter is what is called the roughness factor. For one roughness factor, for the smooth pipe, you have the lowest one. For one roughness factor, you have this. For a higher roughness factor, K by D, you have this, and so on and so forth. Okay, and you can interpolate between this because they are reasonably close by on a logarithmic graph for an estimate, of course. So for the turbulent regime, to find out the friction factor for a given set of flow conditions as quantified by the Reynolds number, you find the Reynolds number, then go to this chart. For the particular K by D value, you find out the friction factor. That's what we normally do. Okay. For the intermediate regime, 2100 to 4000, you see a gap here. That gap is a gap. Okay, it's not well understood. Sometimes it's laminar, sometimes it's turbulent, as we have already seen. We normally avoid design in this regime. We would not like to operate when the Reynolds number is between 2100 and 4000 because we are not really sure of the nature of flow. In turbulent regime, the friction factor is a function of the roughness factor. Now some more explanation of the roughness factor. K is the roughness length or the effective thickness, and D is the diameter of the pipe. And I don't have that thing here, I think. Okay, that's fine. You have a pipe, and if you can idealize the roughness as some sort of projections, you take the projection length, that becomes K, and you divide it by the diameter of the pipe, that becomes your roughness factor. Okay, so that's what it is. So this is the way we approach things, and when we meet next, I'll show you the first application through a problem itself. Okay, as I said, problems are integrated with the learning itself here. You're not just given a separate problem asked to solve as a part of this class. You're given that those as assignments, but you're not given those as a part of this class. This class integrates the problems. You do some, I do some, and sometimes you work out a lot more so that you pick up. They've been designed such that the learning can be more effective. Let's stop here. Let's meet in the next class and take things forward. See you then.